Welcome back to the deep dive. This is the place where we take these huge stacks of research, all this raw data, and really turn it into something you can use. High-level knowledge that gives you the context you need to be not just, informed, but actually ahead of the curve. And today, we are scrapping in for a pretty high-speed journey into the world of AI-driven software development. It's a world that promised us this golden age of productivity, but as we've been tracking, it came with a very sharp and often totally invisible security cost.
It really is a classic paradox of innovation, isn't it? The faster you move, the less friction you want.
Right.
And security, by its very nature, it introduces necessary friction. So what our sources are showing is crystal clear. This revolutionary speed that we get from AI coding tools has created an environment of, really deep and dangerous trust.
And that's what hackers are going after.
Exactly. They are exploiting that trust with tactical precision and, frankly, alarming sophistication. The game has totally changed, and the goalposts for what security even means, they've shifted dramatically.
Okay, so let's unpack all of that and define our mission for this deep dive. We need to cut through the excitement, the hype of this AI boom, and really deliver a clear technical understanding of this emerging threat landscape. So we're going to start by defining the core philosophy that's driving all this, the now infamous vibe coding, because that really defines the target psychology. Then we're going to dissect the anatomy of a major exploit that targeted these exact environments, the Cursor API Trojan Horse. We'll go step by step.
And most importantly,
that's the most important.
We're going to close out by giving you the modern, actionable defense strategies that you need to not just survive, but actually thrive in this new coding reality. Our goal here is to make sure your pursuit of that incredible speed doesn't end in, a complete and total compromise.
I want to start with the concept itself because, like you said, it defines the entire vulnerability. We're in what so many people hailed as the golden age of software creation. And the term that just perfectly captured this fundamental shift, coined by Andrej Karpathy back in February 2025, was vibe coding.
Vibe coding is it's the perfect phrase. It so perfectly captures the psychological shift that separates this era from everything that came before it. It's a development philosophy where the human coder almost completely steps back from the mechanical execution of the code.
They give in to the vibes.
They fully give in to the vibes, yeah. They relinquish all that meticulous, often soul-crushing detail work. The human developer becomes less of a typist, less of a mechanic, and more of an architect or, critically, a product manager.
So instead of thinking about, syntactical correctness or library dependencies or writing all that boilerplate,
all of that's gone.
You're just operating at the level of intent. You describe what you want, you generate the vibe in plain English, and the large language models, the LLMs, they handle all the heavy lifting, the actual implementation. You essentially become sort of detached from the code itself.
And that detachment is the key. The appeal is it's revolutionary. Our sources repeatedly highlight that when you're using these integrated AI tools, things like Cursor or Replit's AI features or these specialized generators like Vercel's V0.
Oh yeah, V0 is incredible.
It's incredible. It can spit out these incredibly complex UI components based on just a few descriptive sentences. And with these tools, the time required for development just shrinks exponentially. We are talking about functional applications that, they once required weeks of dedicated heads-down coding.
Now they're being built in a few hours.
Mere hours, exactly.
This isn't just, a little optimization. This is a quantum leap in velocity. It completely changes the economic model of development. Just imagine for a second, you're tasked with building a complex authentication service. Traditionally, that takes a senior engineer several days, right? To scaffold it, secure it, test it.
At least, yeah.
Now, you just write a prompt to an AI, you review the functional output, and you can deploy a working prototype before you've even finished your first cup of coffee.
Yeah.
That's the magic developers bought into. That's the intoxicating appeal of the vibe.
But that acceleration, that instantaneous gratification, that's what creates the central paradox that we have to analyze here. The moment the developer enters that high-velocity flow state, the human review loop, the friction, it's seen as an impediment, an annoyance.
It gets in the way of the vibe.
It gets in the way of the vibe. And when there is that kind of speed without any friction, there is almost always blindness to the details. This almost reckless acceleration has created a highly dangerous new threat vector because security is, by definition, paying attention to all those little details.
And that is our deep dive mission today. The threat is not theoretical. It's not some far-off possibility. It is specific, it's targeted, and it's highly sophisticated. Hackers are not going after your users directly anymore. They are preying on the fast-paced, trusting nature of these AI-driven workflows.
And they do it by hiding malware inside the very shortcuts that developers are actively seeking out.
Exactly.
And so we're going to look specifically at the architecture of these attacks by dissecting that Cursor API exploit. It is just the clearest, most detailed case study of how this new vibe philosophy provided hackers with a profound and a very high-value vulnerability right in the center of the developer's workflow.
It turns out that incredible speed has a hidden cost.
A huge one, and we're only just now starting to calculate it.
So to really get this, we have to understand the target first.
To fully grasp the attack, yeah, we have to deeply understand the target. Why is the vibe coder so uniquely susceptible to these modern supply chain attacks in a way that, say, the traditional software engineer just wasn't?
I think we need to contrast those two personas really clearly. The traditional engineer, they were a meticulous vetting machine, right? Especially when it came to dependencies. They didn't just type npm install blandly.
No, absolutely not.
Before they integrated any new library, they would absolutely pause their flow. They'd spend time, poring over the GitHub repository, checking the contributor history for anomalies, looking for recent security audits, reading the release notes.
Probably reading some of the source code themselves.
For sure. Auditing a few dozen lines of the source code themselves to understand the core logic. It was time-consuming, yes, but it built this solid perimeter of trust around their code base.
That's the crucial difference. Friction as a necessary security mechanism. The vibe coder operates in a state where momentum is the ultimate goal. They are in that flow state, the vibe, and the AI agent is their relentless enabler. The AI suggests a solution, which often involves some external dependency, installs it, and instantly implements it.
And the developer just accepts it and moves on.
They accept the suggested output and immediately move on to the next feature request. The entire process is streamlined to remove all those unnecessary mental steps.
And here's the core dangerous assumption, right? The coder assumes that the AI, this super intelligent, context-aware entity, has already vetted the package it's suggesting.
Right. Why wouldn't it?
Exactly. Why would the AI, which is supposed to be simplifying and improving the process, lead them down an unsafe path?
But the AI has absolutely not vetted it. This is the fundamental security flaw, which we're calling the trust gap. I mean, most of our well-informed listeners probably get this, but it really bears repeating with clarity. The underlying LLM mechanism is a prediction machine. It is not a security auditor.
It's just playing a word association game on a massive scale.
That's a great way to put it. When you ask the AI to implement a database connection or some complex payment process, it is simply predicting the most statistically likely, the most common token or code sequence required to solve that query based on its massive training data set.
And where is it pulling those solutions from?
From the open internet.
Which is full of junk.
Exactly. It sources solutions from these vast public repositories of open source libraries, places like the NPM registry, PyPI, Maven, you name it. And these repositories contain millions of packages, ranging from perfectly legitimate, rigorously maintained core utilities, all the way down to malicious packages planted years ago, or more recently, packages designed specifically to mimic the legitimate ones.
So the AI looks at, a million examples of database connection boilerplate, sees that 95% of solutions historically relied on a package name, say, dbutil. And it just suggests it. It doesn't analyze the security risk or the maintainer's history or whether dbutil version 4.1 has a remote code execution vulnerability. It just knows dbutil is the statistical answer. It's optimizing for functionality and speed, not for hardening.
Precisely.
Yeah.
And hackers have studied this workflow. They have weaponized this inherent trust by understanding that the attack has to look exactly like the shortcut the developer desires. They know that forcing a vibe coder to stop, check GitHub, and run some manual security analysis, it breaks the flow completely.
Security friction is the enemy of the vibe.
It is the ultimate enemy of the vibe.
So this means the whole lure strategy isn't just about planting a bad package. It's about tailoring the threat to the psychology of that workflow.
Correct. The packages they publish are designed to appeal to two specific psychological vulnerabilities of the vibe coder: speed and cost. So they look like instant optimization tools or packages promising cheap APIs or some form of magic fixer that promises to eliminate a tedious or expensive step. It's basically targeted malware marketing.
That's a scary thought.
It is. If you're coding at breakneck speed, trying to minimize your cloud compute costs or your token usage with your expensive LLM provider. And suddenly, your AI assistant suggests a package promising something like cheapest open AI cursor proxy. I mean, that just short-circuits all critical thinking.
Yeah, you're going to click install.
You are far more likely to install it instantly than if you had to spend an hour manually configuring some complex proxy or researching alternative, cost-effective solutions. The attackers are leveraging cognitive laziness that's driven by an optimization bias.
And that instantaneous acceptance, that one click, is all they need.
That's the foot in the door.
Okay, here's where the rubber really meets the road. We are going to use the Cursor API exploit as our main example because it provides such a high-fidelity blueprint for these modern supply chain attacks targeting the new integrated AI environments. Our sources highlight that this specific technique became highly prevalent. It was primarily targeting macOS users running AI-driven IDEs like Cursor.
Right, but the architectural vulnerability applies to other Electron-based editors as well. It's not just Cursor.
Good point.
And this is a devastatingly effective supply chain attack. We can break it down into 3 distinct phases. Phase 1 is the lure and installation. That's the hook. The attacker's first move is to publish these malicious packages to a public repository. In this case, it was the NPM registry, which is just a goldmine for them because of its ubiquity in modern development stacks.
And the bait, as we said, has to be perfectly calibrated to that target audience.
It is. The specific examples that are cited are packages that claim to offer the cheapest Cursor API or, and this is critical, a free tier for premium AI features. You have to think about the profile. The vibe coder is burning through tokens because they're generating thousands of lines of code an hour. Those compute costs add up incredibly fast.
Oh, the cost-conscious vibe coder, seeing this highly desirable solution pop up in their AI assistant suggestion box, they are just psychologically primed to take that shortcut.
Absolutely. The developer who's operating in that flow state just accepts the suggestion. They run the installation command, a simple npm install malicious package name. And critically, they don't audit the source code, they don't check the package size, they don't look at the post-install scripts. They just trust the process.
And the package gets installed in the local node modules directory.
And the hook is now set deep inside the system.
Okay, that brings us to phase 2. Infection and exploitation. And this is the truly sophisticated part, the thing that distinguishes this attack from just, simple file download malware. The sources really emphasize that the trap is sprung not upon installation, but the next time the user opens their IDE. So why is the IDE launch the critical trigger point for execution?
It executes upon IDE launch because the installation script, which runs immediately after the package download, it doesn't need to run the final malicious payload right away. It just needs to insert a small, inconspicuous piece of code, a hook, into the IDE's startup sequence.
And this is where the architecture of the IDEs themselves comes into play.
Yes, specifically the fact that so many of these popular modern IDEs are built on the Electron framework.
Okay, we need to dive deep into that Electron detail. For our audience who might not be familiar with the specifics of application frameworks, why does using Electron specifically matter so much for privilege escalation and security?
Well, Electron allows you to build desktop applications using standard web technologies, HTML, CSS, and JavaScript. The application essentially bundles a Chromium browser engine and the Node.js runtime environment. Now, because these IDEs are meant to perform really complex system-level tasks, they need to compile C++ extensions, access your entire file system, execute build scripts, interact directly with your operating system. They run with fundamentally high privileges.
They're not sandboxed like a web page is.
Not at all. They operate outside the tightly restrictive sandboxing protections that a standard web browser or a traditional mobile app would enforce.
So if that malicious package is installed, the hook it sets in place executes the moment the IDE launches. And that code is then running within the Node.js context of the IDE itself.
Precisely. The code executes with the same high privileges as the editor application itself, which means it has direct programmatic access to the underlying operating system's file structure via the Node API. It doesn't just sit there inertly in the Node modules folder, waiting to be called by application logic.
It's alive.
It actively starts reaching out to the system immediately upon IDE initialization, completely bypassing standard operating system or antivirus security barriers that expect malware to come from some external, unauthorized source. In this case, it's an authorized application launching unauthorized code with elevated access.
So that initial execution thread is the beachhead. And once that's established, the malware moves into phase 3, the payload. And our sources break this down into a just devastating three-pronged attack designed for maximum data exfiltration and persistence.
That's right. The first prong is the immediate priority: credential theft and data exfiltration. The script runs an instantaneous scan of the entire development environment.
And what are they looking for? Where are they looking?
They're looking for the low-hanging fruit, the places where developers always store secrets, even if they know they shouldn't. So this includes common spots like .env files, which hold local environment variables, and shell configuration files, things like .zsrc, .bash profile, and .jitconfig. They look for API keys that are cached in application storage or in local developer credential stores.
And the primary goal here isn't just generic passwords, right? It's the high-value generative AI and cloud access keys.
Exactly. Keys for OpenAI, Anthropic, AWS, Google Cloud, Azure. These keys are currency. An attacker who gets these gains instant, unauthorized access to massive compute resources and sensitive corporate data stored in the cloud. These keys can be resold on dark web markets for staggering profits, or, and this is perhaps even worse, they can be used by the attacker to train other malicious models at the victim's expense.
Wow.
Yeah, generating more potent, personalized social engineering tools or custom-built hacking utilities.
So that covers the immediate profit motive. But prong two is where the attack moves from just theft to deep systemic control.
Yeah.
System-level modification.
This is the true Trojan Horse element, and it demonstrates some really advanced tactical thinking. The malware targets the very heart of the development environment. Specifically, it seeks to overwrite critical system-level files within the IDE itself, such as Cursor's main.js file.
And since we established that these editors are fundamentally Node.js JavaScript applications, the main.js file is the primary startup script. It's the brain, the core logic of the entire editor.
It is the brain. So by compromising main.js, the attacker effectively owns the editor itself. They can view the developer's workspace as if it were their own.
That's terrifying.
By injecting just a tiny piece of malicious code into that main.js file, the attacker gains the ability to monitor and control virtually every single interaction the developer has with their IDE. We're talking about key logging, seeing every keystroke, observing every line of code generated by the AI assistant, monitoring every project opened, every connection made, and every file saved.
So it's not just about the developer's machine anymore.
No. This allows the attacker to compromise not just the developer's local machine, but potentially every single client project they are actively working on. It turns the IDE into a persistent, invisible surveillance platform.
It's the ultimate act of betrayal, turning the most trusted tool in a developer's arsenal into a spy. And the third prong, you said this is critical, it ensures this surveillance continues indefinitely, gaining persistence.
Yes, this is a crucial tactical move that often gets overlooked. Once main.js is poisoned, the malware has to ensure it doesn't get cleaned up by legitimate system operations. So its final action is to disable the IDE's auto-update mechanism. Developers rely on automatic updates for, feature parity and, most importantly, security patching.
But if the IDE runs an update, it would naturally overwrite the compromised main.js file with the clean version downloaded from the vendor. That would kick the attacker out of the system.
Exactly. So by blocking the updates, the developer is left running a permanently compromised zombie version of their editor. The attacker has locked in their foothold, ensuring long-term control and continuous monitoring of a high-value target, until that developer eventually, maybe, figures out the IDE is behaving strangely or the entire system is manually rebuilt from scratch. This level of persistence makes the Cursor API exploit a really stark warning about the new depth of supply chain risk we're facing.
That detailed breakdown of the attack it's just terrifying. But it points to these deeper systemic weaknesses in the whole vibe coding methodology itself. Why are these high-velocity workflows, just by their nature, such perfect targets for exploitation?
We've identified 3 core vulnerability factors that really compound the problem. The first, and probably the most easily understood, involves the quality of the generated output. It's the factor of unvetted code and the holes it contains.
This is where our sources use that fantastic analogy.
The Swiss cheese architecture. The code is syntactically correct. It's fast, it's functional, it works perfectly, often on the first try. So on the surface, the block of code looks absolutely solid.
Right.
But security experts call it Swiss cheese because beneath that working surface, it is just riddled with critical security holes. It's solid on the outside, but it's full of these structural weaknesses within.
And this all stems from the illusion of correctness. The developer is just so thrilled that the AI solved a complex task instantly, like, for example, a custom API gateway function. that they completely skip the necessary steps of checking the underlying security implementation.
Let's use some concrete examples. An AI is asked to generate a login system. It will deliver a database connection, user hashing, and a session management function. It looks beautiful. But it might completely fail to implement crucial defensive measures like, say, rate limiting on failed login attempts, or necessary input sanitization on the fields.
Which instantly opens the system up to brute force attacks or common injection vulnerabilities.
Instantly. Another common example. An AI generates a file upload feature that works perfectly. It lets a user upload a PDF, but it fails to implement strict file type validation on the server side, meaning an attacker could just upload an executable file and potentially compromise the entire server if that file is ever executed.
So the programmer assumes the AI wrote secure code, because that's what a senior engineer would deliver.
Yeah.
But the AI was only trained to write example code.
Right. The statistically most likely functional solution, not necessarily the most hardened, production-ready solution that has had all these security considerations baked in from the start.
And the hacker targets this assumption gap.
Exactly. A human security expert might write, say, 5 lines of business logic and then 15 lines of defensive hardening around it. An LLM, because it's optimizing for the shortest path to functionality, writes 10 lines of business logic and 0 lines of defensive hardening unless you specifically and often repeatedly prompt it to do so.
Okay, so that's the first factor. The second major vulnerability factor you mentioned is the exponential rise of agentic tools. Let's define agentic again, because this is where the vulnerability really scales beyond just simple code generation.
Agentic refers to AI systems that are given a high-level goal and then have the autonomy to plan, execute, and troubleshoot multiple steps to achieve that goal entirely on their own. And often, they're interacting with the outside world.
So the command isn't just write me a login function. The command is more like set up a complete backend for this new application, use a relational database, integrate the Stripe API, and then deploy it to the staging environment.
Precisely. The agent doesn't ask for permission for every dependency selection or for every configuration file it writes or for every database connection it sets up. It autonomously selects libraries, sets up infrastructure as code configurations, and establishes all the connections.
And the sheer speed of this execution, it just outpaces a human's ability to comprehend the totality of the changes that were just made to the code base and the infrastructure.
That is the agentic blind spot. In a 5-minute execution sequence, the agent might select a deprecated library that it found highly ranked in the open source repository, maybe due to high historical usage, even if that library is known to have vulnerabilities.
And the developer misses it completely.
They only see the final working output. They miss that library selection entirely. Worse still, if the agent uses an insecure default configuration, for example, accidentally configuring a public AWS S3 bucket for file storage, or hard-coding connection secrets into a configuration file because it was the easiest way to make the script pass, the human developer is just. They're unlikely to catch that vulnerability until a penetration test, or until a malicious scanner finds it first.
You're not just auditing a human's work anymore. You're auditing an autonomous system's rapid, multifaceted, and often completely undocumented decisions across both infrastructure and code layers.
Which leads us directly to the third factor, the scanner arms race. This is the ultimate escalation. It's AI against AI. Our sources confirm that just as developers are using AI to accelerate writing code, sophisticated hackers are using equally automated scanners, often LLM-driven themselves, to accelerate the search for these vulnerabilities.
So these aren't just broad, opportunistic attacks anymore. These are targeted probes specifically looking for the artifacts and fingerprints of vibe coding.
That is precisely right. These malicious scanners are actively trawling public repositories like GitHub, GitLab, and other code-sharing platforms. They are looking for specific, non-random, telltale signs of LLM generation. They're looking for artifacts that human-written code typically just doesn't exhibit.
So what are those specific signs? The fingerprints of AI-generated code.
Well, they look for several indicators. First, you have unique comment structures or boilerplate text that specific models often append to their output. Second, the heavy use of standardized, often overly generic variable names.
Like tempvar or data array.
Exactly. Tempvar, data array, process result. These are common across specific LLMs because they optimize for clarity over creativity. And third, and this is the most critical, they look for the distinct lack of security hardening, the absence of defensive coding patterns, or the failure to correctly implement error handling for security contexts. The scanner sees this pattern generic names, boilerplate structure, and a glaring security omission, and it flags it as high-probability vibe code.
So if a scanner finds a project with 90% generic variable names and, say, a login function that lacks any implementation of a recognized security library for rate limiting, that's a bright red flag saying this project was written by an AI and it's almost certainly vulnerable.
Exactly. And once it's identified, the scanner doesn't stop there. It then starts probing that target repository for known weaknesses that are specific to that LLM's coding style. For instance, the research cited a known tendency of some of the older GPT-4 models to hallucinate insecure regex patterns when they're asked to validate user input.
So if a hacker knows an LLM tends to write bad rejects,
They'll specifically test for that known vulnerability in these identified vibe-coded projects. This is a highly focused and automated hunt for the AI's predictable flaws, turning the LLM's very efficiency into a massive security weakness.
we've established the magic, the menace, and the devastating anatomy of the attack. But the necessary conclusion, as our sources really emphasize, it's not to stop using AI. The genie is not going back into the bottle. The economic benefits are just too vast.
No, absolutely not.
The solution is to fundamentally change our relationship with it. We have to transform ourselves from these passive acceptors into active collaborators.
That's the critical mindset shift. We have to establish a new core principle. We are moving from the legacy security attitude of trust but verify to the new necessity of verify then trust. You must actively prove the code is safe through rigorous documented verification before you allow the AI's output to enter your system or, God forbid, your production environment.
Okay, let's turn this theoretical shift into some actionable steps. These are the defense strategies that need to be implemented immediately in any high-velocity AI-driven workflow.
The first one, and this is arguably the most difficult piece of advice for the vibe coder to accept, is also the most effective defense. Review the code. You have to have a human in the loop.
We have to intentionally reintroduce friction where it matters most. And it's hard, we know that. Going from zero friction back to having friction, it's painful. But this friction is now our first line of defense. We can no longer forget the code even exists. If an AI generates 1,000 lines in 5 seconds, you still have to read the comparison of what was there versus what the AI added before you commit that code to the repository.
You don't have to write the code anymore, but you must take ownership of it. And this means using specialized diffing tools that are optimized for reviewing these large AI-generated blocks. When you're reviewing a function, you have to understand not just what it is doing functionally, but how it handles common attack vectors.
And if the AI suggests a new import,
You have to pause the flow, Google it, and verify its legitimacy. Furthermore, you should engage the AI itself in a security review. If it writes a complex security-critical function, prompt it to explain the security implications and hardening steps you took, or identify 5 potential attack vectors in this code block. That forces the AI to reveal its own blind spots, and it will often self-correct or add necessary defensive logic.
the second strategy directly addresses the lure we saw in that cursor API attack. Be skeptical of cheap tools.
This is non-negotiable, and it's rooted in basic economics. There is no free lunch in the API or cloud compute economy. If you're using premium AI services from major providers, they cost money, full stop. If a third-party NPM package suddenly appears claiming to offer cheapest access or a free premium tier to services like OpenAI, Anthropic, or AWS Compute, you have to treat it as an almost certain scam or a Trojan horse.
The attackers are just leveraging the developer's desire for shortcuts and cost savings, knowing that high velocity often means high token consumption and high bills.
And that few dollars you might save on tokens or compute time is simply not worth the complete compromise of your development machine, the exfiltration of all your credentials, and the potential compromise of your client's data. Stick strictly to official SDKs and packages that are directly provided or rigorously verified by the service provider. If you must use a third-party package, you have to assume it's malicious until you can prove otherwise.
Okay, so next, we have to acknowledge that the human eye is going to miss things, especially in these high-velocity sprints.
Yeah.
And traditional perimeter defenses are not enough because the threats are coming from the inside, from the supply chain and the code generation itself. So we need intelligent defenses that are built for this new workflow. Deploy modern security tools.
Yes. Our sources highlight that traditional static analysis security testing SaaS tools, which scan code after it's written, they're often just too slow and too disruptive for the vibe coding workflow. You need tools designed to work with the speed without introducing that bad kind of friction. This is where tools designed for the nuances of AI-integrated development environments really come into their own.
One tool that's been repeatedly highlighted in the context of securing these environments is aikido.dev. Can you elaborate on how a tool like this tackles the specific problems we've discussed, particularly this need for zero-friction security?
Well, Aikido and tools like it, they understand that security cannot interrupt flow. They're built to interact intelligently with the speed of the AI generation process. A key feature that was cited is their Zen embedded firewall. This is critical because it offers security without stopping the coder. It's an embedded gatekeeper that operates in the background of the development process.
So how does this Zen firewall mechanism operate? Where is the friction removed?
It doesn't stop the AI from generating the code. Instead, what it does is it analyzes the generated code in transit, either during the runtime execution context or as the code moves toward the compiler. Because it's so deeply integrated with the IDE and the local environment, it can act as a real-time policy enforcer. For instance, if the AI unknowingly generates a code snippet that attempts a malicious injection attack,
Which we know it can do.
which we know it can do. Or if a newly installed Trojan Horse package attempts to make an unauthorized network call to an external server to exfiltrate data, the firewall intercepts and blocks that specific action instantly.
So it's preventing the malicious code from ever executing on the machine or connecting to its command and control server, all while the developer is still coding. It allows the vibe to continue. The malicious action is stopped, not the development flow.
Exactly.
That addresses the runtime environment, but what about the source of the infection?
That leads directly to the next critical step. Manage your supply chain. We have to audit the packages before they ever enter the IDE environment. Before you blindly type npm install, you need to perform some basic pre-installation verification. This requires just an instant audit, pausing the flow for maybe 30 seconds to check 3 red flags.
Okay, first one, the download count and popularity.
Correct. Popularity builds some level of confidence. If a package has millions of downloads and is widely used across the industry, it's not a guarantee, but it does suggest a community review has taken place over time. Conversely, a low download count for a package that claims to be some essential utility is a massive red flag.
Second, the maintainer's history.
You need to check the maintainer's profile. Is this a new anonymous profile created last week, or has this person been contributing to the open source community for years? A history of legitimate contributions adds a lot of verification.
And third, the created date. This seems like the most glaring, simple red flag.
Absolutely. A package claiming to be the new core logging utility for Node.js that was created 3 days ago should trigger an immediate manual investigation, no matter what your AI suggested. The age of a package, contrasted with its perceived importance, is often the easiest indicator of a newly planted Trojan horse that's trying to capitalize on a high-traffic search term.
And finally, probably the most important piece of developer hygiene, amplified by AI. Secure your API keys.
This is the cardinal rule. It has existed for a decade, but it is now even more critical because AI models actively work against you here. Never hard-code API keys or secrets into your application code, even if it's just for a quick prototype or a test.
And why does AI make this harder?
Because LLM models, since they're optimizing for immediate convenience and fast functionality, they often prioritize placing keys directly into variables or configuration files just for simplicity in the generated boilerplate. If that code block ever touches a public repository, or if your local system gets compromised by the kind of malware we've been discussing, those keys are gone instantly.
So what are the best practices now?
They remain firm, but they require strict adherence. You have to use robust environment variables, .env. You have to ensure your .jitignore file is rigorously configured to exclude all sensitive files from ever being committed to a public repository. And, crucially, you should move towards specialized secret management tools and vaults that are integrated into your CI/CD pipeline, rather than relying on local configuration files.
In rotation.
And finally, yes, given the prevalence of credential theft, rotation is mandatory. You have to treat your API keys like temporary access tokens. If you have any suspicion at all that a package has compromised your environment, revoke and rotate those keys immediately. They are the gateway to your most expensive cloud compute and data stores, and they are the prime target of this new wave of attacks.
This has been a fascinating, really deep dive into a landscape that is just changing daily. Vibe coding is, without question, a powerful, transformative force. It's democratized creation, it's lowered the barrier to entry, and it's delivered unprecedented velocity to developers worldwide, allowing for rapid iteration and incredible new services.
But that acceleration comes with a profound and often hidden trade-off. It has simultaneously lowered the barrier to entry for creators and the barrier to being successfully hacked. The Cursor API attack is not an isolated incident. It's a stark architectural warning about the danger of abdicating understanding and verification for the sake of speed. We must never allow the convenience of the tool to replace the rigor of the developer.
It seems clear that the future of coding is inherently collaborative, but it's a collaboration where one partner, the LLM, is incredibly powerful, utterly reckless when it comes to security, and requires constant human supervision.
Collaborative vigilance has to be the new standard. By reintegrating that necessary human review loop, applying intense skepticism to third-party tools that promise unreal savings, and deploying specialized security software designed for this new age, developers can reclaim control over their increasingly autonomous workspaces. Speed is power, yes, but security has to be foundational.
So what does this all mean for you, the listener, as you dive back into your development projects? The core question we are left with, and our final provocative thought for you, is this. In this new accelerated reality where code creation is instantaneous and often invisible, how do we balance the joy of that instantaneous creation with the foundational, ethical, and necessary need to know exactly who or what we are truly collaborating with inside the most privileged parts of our systems? We have the power to create at light speed, but do we still have the wisdom to secure what we build? Think about that the next time your AI suggests an exotic, unverified dependency.